Yeah, I walked in with my. I was like,
Where'd you
get
get
that?
Alright, we're gonna talk about functions a little bit more.
Good. I'm so glad.
I know you've been waiting all morning for this.
Yeah. Oh yeah. I've been dying to talk about. I've been waiting to take a nap.
I'm gonna learn about vectors.
Huh? Vectors?
Physics is so boring.
Vectors are fun.
That'll
I said
help
I've
with
been waiting to take a nap.
physics right now.
Physics is terrible. I said I'll be waiting.
We have a little time at the end, I'll teach you vectors.
Yay!
You want to teach physics?
No.
Why not? You probably be better at it.
Be hailed.
You're right. You probably explain it
Okay.
better. We already did this.
Shut up!
Okay, I'll just leave.
Dude, I got a port.
I'm just gonna tolerate any part. Because I know people are hard to teach. I'm gonna be someone that never did. Or I'll be Rebecca.
I'm gonna be.
Alright, so we talked about this yesterday. What a function does visually, try to give you an idea. Visually, a function takes an input value, okay? And that input value, instead of calling it an input value, we call it a domain value, okay? And then essentially it's just your x values that you're going to plug in, okay? The function is some rule, some algebraic rule that is going to change and alter that input value, okay? And how it changes it, ultimately it's finally going to give you one singular value as an output, and we call that output value a range value, okay? But kind of drawing comparisons, domain are your x values, range are your f of x values, or maybe in algebra 2 you said, well, that's the same thing as y. I don't have a problem with you doing that, but what I want you to understand is that in a course, when they give you a rule and they say y equals this rule, you don't know if that rule is a function yet. Does that make sense? And you have to go through the preliminary steps of determining whether it's a function or not. Okay? But if they give you f of x is equal to that rule, you automatically know that whatever they're talking about in that rule does abide by this function definition. Does that make sense? Okay? And it's going to be nice because there are going to be things that we do with functions that you can't just do with any other maybe equation, okay, or graph. Okay, like if y equals, let's do it this way. If I say like x equals y squared, okay, I don't know right away off the top of my head, if it's the first time I'm doing this, whether that's a function or not. Okay, but when I say f of x equals x squared, I know automatically, because I'm using that notation, that this is a function. Is it going to make sense? Okay. This one would not be a function because it ends up looking like this. Okay. And when I have an x value of, say, 4, okay, think about this. If I solve this, square root both sides, I get y equals square root of x, right? Okay, but plus or minus, I would get 2 there or negative 2 there. And the reason this would not be a function is because what's happening is that we're taking a value of 4, and it's saying that that value of 4, if I'm using this mapping idea, that value of 4 comes over here to a value of 2, but it also comes over here to a value of negative 2, and that's a problem with how we define a function. A function says that for every x value, for every single x value, there is one and only one y value. And here we're seeing for this particular x value, we're getting 2 y values, right? Or 2 range values, okay? So as a mapping, just in general, for any type of function, we're going to start with an x value over here, or a domain value, okay? And it should then be paired up with an individual y value on the right-hand side, okay? So maybe this is like 7, and maybe I've got 2 over here, and it goes to 9, and maybe I got negative 3 over here, and it goes to 4, okay? I've got For every one of these x values, there's one and only one y value. Okay? Now, here's the situation. I could have, like, let's say I put another number here, let's go 0. Let's say 0 goes to 2 as well. Okay? So 4 goes to 2, and 0 also goes to 2. That's okay. Okay? Because for every x value, for every time I plug 0 in, do I get one y value back? I get 2 back, right? Okay. It's okay for these f of x values to be paired up with multiple x values, but you can't have multiple x values being paired up with one y value. Okay. And the idea of that is, if we were to, draw just a kind of messy. Start over. If I were just to take the function f of x equals x squared, right? Some ordered pairs that exist on that function. Obviously, we got 0, 0. We got maybe 1, 1. We got 2, 4. And we also have maybe negative 2, 4, don't we? Okay. And there's going to be an infinite number of values that do this, or pairs that do this. But if I look at those two things right there, if I think about the x values that come from a set A, and my f of x values that are in set B, okay, I think about my rule of x squared, okay, if I take some value 2, it should go to 4, right? If I take some value negative 2, it also goes to 4. Okay, so that's kind of the image that we would get from thinking about that rule, and that's okay, because we still have one x value paired up with one and only one y value. Okay, it's okay that these two things are going to the same y value, because we still, if I look at this parabola here, okay, if I tell everybody, and this is the reason why we have functions and we classify them separately than other things, is because if I tell everybody, look at the y value, or look at the f of x value that pairs with 2, does everybody look at the same number? Is everybody looking at 4 when I say that? Okay. And if I say, everybody look at the f of x value that goes with negative 2, again, everybody's still looking at 4, right? Okay. But going back to this graph, okay, if I say everybody look at the y value that's paired up with 4, do some people look at positive 2? And do some people then look at negative 2? That kind of, you can see the issue there, right? And we want to make sure that we don't have that issue. We want to make sure that when I say, hey, what's the y value that goes with this x value, you can all give me 100% of the time the same exact value. Okay? And then we find out if we classify things that way, so they abide by that rule, there are some other characteristics, some other neat features that occur with functions that may not occur necessarily all the time with other things. Okay? And when I say other things, I'm talking about other rules that basically take some x value and some y value and relate them somehow. Okay? Whether it be y squared equals x or something like that. Still taking input values and getting output values, but how they relate with one another might be different than how they normally relate with a function. Okay? Is that all right? Okay. So what we like to do, and you're going to see this in every single chapter we go through, we're going to introduce maybe a couple different types of functions per chapter. Okay. We've talked about this before. We've already talked about quadratic equations, and we'll talk about them as functions here soon. But we're going to talk about quadratic functions. We'll talk about cubic functions, quartic functions. And we kind of talk about all of those inside one chapter. Okay. But then once we start talking about those and analyzing those and understanding what they look like, how we develop them, one of the first things we like to do is think about what is the domain of those types of functions. Okay? And then we go to the next chapter and talk about rational functions. Okay? Being, rational means ratio, right? So things that are divided by one another. Okay? So we have fractions in our function rule. one of the first things we like to do is think about, okay, what is the domain of these types of functions, and how do we address that domain, okay? Because what we're interested in is ultimately how to graph these things, and as long as I know what x values I'm allowed to choose, I can plug those x values in and get f of x values or y values back, right? Okay, and that's going to help me create ordered pairs to graph. And then we go to logarithmic functions and exponential functions, and we talk about the domains first. And then we go to trigonometric functions, and we talk about the domains. Okay, so my hope is that you realize domains are things that we're going to introduce it now, but it's something that's going to kind of be progressive throughout the entire year. Okay, it's going to be something we use all the time. And in the past, I don't know if I've mentioned that in other classes. I just sitting back and thinking that a lot of times in mathematics, maybe we don't realize, especially in a math course, we don't realize the importance of a concept until 6-7 weeks down the road, and we've used it for 6-7 weeks. And it would have been real nice to learn that on the first day, right? Okay, instead of having to worry about learning it on the 7th week. So I know it's going to be something that you're going to need to use a lot. So I want to make sure that we kind of develop a good understanding for it now, so it'll make the rest of the course a lot easier if we understand this idea of domains. We're going to be interested in whenever we have a function. So what today is just looking at some functions and talking about how can I pull a domain out of that function. Okay. So let's say I give you like f of x. We'll just start with one that's really easy. Let's just say 2x plus 3. Okay. That's a function. It's a very boring function. It's just a line, right? Okay. But if you think about a line, think about graphing a line. In Algebra 1, we talked about a line being something that extends in all directions, or both directions, I guess, forever, right? Okay. So if I graph like 2x plus 3, maybe it looks something like that, right? Okay. And graphically, what that's telling me is every one of those points, every one of these things on here, there is an associated x value that provides me then an f of x value, right? Or provides me a y value, okay? So it tells me that no matter what I plug in for x, I can always double it. Think about any number on the real number line that you can imagine, can you always double it? Okay? And then you always add 3 to that result. Yeah. Okay? So you're always, no matter what you plug in, you always get something back, right? And that's kind of what you want to think about when we're doing this domain kind of analyzing process is, are there values that when I plug it in, I don't get something back? Okay? Because those are going to be restrictions or issues that we want to talk about. So here, I can take any number I want to, plug it in right there, double it, get a number, add 3 to it, get a number. I get an output. For every value, I get an output. So my domain, there's a couple different ways of writing this, but my domain is x such that x belongs to all real numbers. Okay? Or in interval notation, a lot of times we say domain negative infinity, positive infinity, or domain is all real numbers. So those are 3 different kind of notations that you'll see on a consistent basis. I think for the most part, WebAssign is going to use that middle one with negative infinity and positive infinity, but they're all acceptable. They all say the same thing. And a lot of times you'll see domain being asked with a capital D, and then they put a colon after it. Okay, range would be a capital R with a colon after it. But that's kind of what we want to do. Every time we see a function, okay, or I guess not a function, a function. Every time I see a function, I want to think about, first, I make the assumption that all real numbers are my domain. And then we start going through there systematically and say, okay, which numbers can I keep and which numbers can I kick out? Okay? And ultimately, there's going to be a couple situations where you kick things out. And that's kind of the focus of today's lesson, is to realize what are the 2 main types of functions that we have to remove values from, okay? From the domain. So let's just say I start with like 2x squared plus 3. Now I've changed it, right? Now it's non-linear, okay? It's a parabola, right? Okay? Think about any number, so we're going to make the assumption first that the domain is all real numbers. Okay? That's the assumption we make. And then I start thinking, okay, do I violate any algebraic rules? Does anything happen here that when I plug an x value in, I do not get an output value back? Okay? So thinking about any number you can ever imagine, if I square it, do I get another number back? Yeah, get a real number back, right? And if I take that number, which is a real number, and I double it, do I still get a real number back? And if I add 3 to it, do I still get a real number back? So this is got a domain of all real numbers again. Okay? And what happens, if you remember this format that we talked about, I don't remember what day it was, it's about a week ago, maybe a little bit more than a week ago. I gave you something like this. Remember that? Okay. That's just the general generic polynomial function. Okay. So anything, no matter what the exponent is, as long as the an integer, okay, positive integer, okay, we'll have something like this. So 2x squared plus 3 is of this form. 5x to the 7th plus 13x squared plus 9 is a form of this. Okay. Whenever you have something polynomial, even that 1 to the first power, 2x plus 3, that's of this nature. Okay. Those types of functions will always, 100% of the time, have a domain that is all real numbers. You can always plug in any value you want and get an output value back. Okay? So it's kind of a characteristic of that category or that grouping of functions. There's an infinite number of functions in there, but we can, if they follow this format, we can automatically say that they have a domain of all real numbers. Okay? Meaning then that regardless of the x value I choose, I will get an f of x value back. Okay? And I will have that rule, that definition, I guess, that was defined as for every x value there's one and only one y value. All those x values of the infinite x values that exist, every time I choose one of those and I plug it in, I get a y value back. So for instance, if I plug in 10 here, I'm going to get 23 back, right? Okay? Well, if I plug in 10 200,000 times more, I better get 23 back 200,000 times more. Does that make sense? I'll never get a different value back other than 23. And then hopefully that's pretty obvious, pretty evident, but it is one of the main features of a function. So what happens? Well, where are there issues? And you might be saying, well don't I just have domain being all real numbers for everything? What is the number one rule that you think about or that you've been taught throughout high school that you cannot do in algebra? Have 0 in the denominator. You cannot divide by 0. So let's create a function that has that. Okay, so ultimately what's going to happen is in order to get 0 on the bottom, we have to have some type of expression in a denominator. Okay, so I don't care right now, let's just say the numerator is, let's just make it 3. And let's put the denominator as x minus 6. Something like that. Okay? And you can start thinking about, okay, I'm going to make this assumption first. Always make the assumption. You always start off saying you can plug anything in. Okay? But the hope is that we realize that here, this type of function is a little bit different. Because there's a situation, I start plugging x in, maybe x is 1. And I get 3 over negative 5, that's fine. If x is 2, I get 3 over negative 4, that's fine. X is 5, I get 3 over negative 1, that's fine. But when x is 6, you get 3 over what? 0. 3 over 0. And that's not fine, right? You have an issue there. Okay? Now what happens, hopefully you can recognize, you can visualize that, yeah, that had to be 6 because that's when we get 0 on the bottom. But what we do with functions like this, because it might not always be linear, okay? It might be a quadratic, it might be a cubic, it might be a root function or something like that. We'll talk about those here in a little bit. You take the denominator and you just come over to the side and say, here are my issues. This is where I'm going to do my work for finding domain problems. So I'll say x minus 6. Okay? I want to know when that is equal to 0. Okay? Because that's going to provide me a problem down here at the bottom, right? It's going to divide by 0. Okay? So a lot of times I'll go to the side and I'll just do x minus 6 equals 0. But really what we're thinking, or we should be thinking, is that I'm doing work and I'm finding out numbers that x cannot be. Okay? So we're saying x minus 6 cannot be 0. Does that make sense? Or cannot equal 0. So now if I solve that, and I'm just going to, even though I make that non-equal sign, I'm going to still solve it like an equation. Okay? But every time I go through the process, I'm going to leave that as a not equal to. So add 6 to both sides. It automatically tells me that x cannot be 6. Okay? So what we do is we make the assumption of all real numbers. We go through that work, and now we have a little bit new information. So we put a semicolon, and we say x cannot be 6. And that's how we would write that in set notation. Okay? Again, I think that's probably maybe the easiest way to write it, because it's more informative. There's a lot more information here, x such that x belongs to all real numbers, but x cannot be 6. Okay? But a lot of times, again, we want this to be an interval notation, right? Okay? So to take this and put it in interval notation, it might be a good idea to draw a quick number line. Okay? And think about the numbers that you're allowed to use. Well, we're allowed to use anything except for 6. So I'm going to find 6 on my number line. I'm going to put an open dot on there, because that's what that tells me, right? An open dot says you can't choose this value. There's a problem here. But we can choose anything to the left of 6, and we can choose anything to the right of 6. Because any of those numbers, even 5.9999999, as many times as you say 9, minus 6, is still going to give me something back, right? It'll give me a number very, 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 very close to 0, but that's okay, it's fine. Okay, it gives me a numerical quantity back. It gives me a real number back. Okay? So we want to be able to, in interval notation, write this. Okay, so we always read interval notation from left to right. So what is the first number over here on the left-hand side that we're interested in? Negative infinity. Okay? And now I start moving, okay? And I get right here to 6. And we know we can't use 6, right? So the last number that we would be able to use on that left-hand side is 5.9999999 forever, right? And if I can, obviously, hopefully we realize we can't write that down, okay? And if I did write that down, and I thought I was done, somebody could pick my pencil up and put another number on the end of it, and they now have a number closer to 6 than what I did, right? Okay? So we can't physically write that number down, so we write 6 down, and we use a parenthesis to tell everybody that that 6 with the parenthesis really means that 5.999 forever. Okay? The number that's closest to 6 that we can get to. Okay? We jump over 6, and now we want to talk about 6.000, as many zeros as you can think about, and then tackle 1 on either that, okay, or whatever other number you want to. Okay, and that's going to be the number directly to the right of 6, right? We can't write that number down for the same reason we couldn't write 5.999 down. So we're going to just start with 6, and that parenthesis there tells us that we're starting really with the number that is directly to the right of 6, the real number that is the first one after 6. And now what would be the last number we come across here? Infinity. Okay? Now what we're saying is that numbers for this x minus 6, numbers that work for this function, are all of these. They could come from this range here, okay? Or they could come from this interval. So what is the notation we use for the word or? Union. Okay, so we union those two things together. Alright? And that's just the interval notation way of kicking out one number that is your number line. Okay, as you think about that, that is every single number on my number line except for 6. Okay? And we need to make sure that we are able to do this, because what's going to happen is when we start graphing that type of function, that's the first thing we're going to look at, and we're going to do a graph. And we're going to remind ourselves graphically, hey, we can't do anything here at x equals 6. So we'll draw the vertical line, on x equals 6, and just remind ourselves visually, nothing's going to happen here. There's no y value that's going to get plotted here, because there's an x value here that we can't use because we have 3 divided by 0. Is that all right? Okay. So let's do another one. Let's do make it a little bit more difficult. Let's go f of x is equal to let's go x plus 5 over let's go x squared. Minus 5x minus 36. So if we do that function, x plus 5 divided by x squared minus 5x minus 36. Okay. First thing I want you to look at is that top, that numerator. Okay. Will you ever have an issue with that numerator? Can you take any number you could ever imagine, plug it into that numerator, and add 5 to it, and still get any number you can imagine? Yeah, okay. So that numerator, there's no problems there, okay? You're going to get always, whatever x value you choose, when you plug it in here, you'll always get something back for the numerator, okay? But the denominator, okay, we have problems with that denominator because, you know, if I chose, and you're going to see this in a moment, I think it's negative 9. If I choose, or sorry, positive 9, okay, I'll get a number up top. I'll get 14 up top, right? But on the bottom, I'll get 0. 14 divided by 0 you can't do, correct? Okay. So we need to talk about what values we can't use here. So I'm going to take x squared minus 5x minus 36 cannot be 0. Okay, denominators can never equal 0. So now, quadratic equation, okay, you can solve that using any technique that you feel comfortable with. Could be quadratic formula, could be complete and square, A times C method. This case is probably the product with sum technique. Eventually it'll be the rational root theorem. There's going to be a lot of stuff that we learn kind of progressively throughout the course that will allow us to make this denominator a lot more difficult type of thing to factor. But right now, hopefully you see that that's going to factor to x minus 9 and x plus 4, right? And that cannot equal 0. So just like normal, I'm going to take x minus 9, cannot equal 0. X plus 4 cannot equal 0. So x cannot be 9, and x cannot be negative 4. Okay? Even though they provide me a number in the numerator, if I use 9, I get 14 up top. If I use negative 4, I get 1 up top. Both of those will give me a 0 on the bottom. So I have 14 divided by 0 or 1 divided by 0. I can't do that calculation. Okay? So those are my issues. So here, when we write our domain, again, we're going to say x such that x is an element of all real numbers. Okay? However, x cannot be 9 and negative 4. And usually we just separate it. If there's multiple things it can't be, we just separate it with a comma. But that's the set notation. So if you ever see something like that, sometimes they might write it this way. They'll eliminate or leave out the x as an element of all real numbers. And if they do that, it's kind of like an understood statement that, you know, I'm just kicking out from the real numbers, the numbers 9 and negative 4, everything else will work. I like this because it reminds us, to put that in there, it reminds us that we're not dealing with imaginary numbers. And that might be a situation that when we do this work here, maybe we do get imaginary numbers. And that would tell us maybe what we can do with those numbers, those results. But now if I put this in interval notation, thinking about our number line, okay, the issues arise at 9 and negative 4. Okay, so there's going to be an open dot on both those. But everywhere else we should have a solid line segment, or a ray. Okay. So now going through here left to right, what would be the first number over here on the left that we can use? Negative infinity. And we're going to get up to just to the left-hand side of negative 4, right? So I'm getting up just to the left-hand side of negative 4. I'm going to use negative 4, but they don't put a parenthesis on it, right? Okay. And that tells me I can use numbers like negative 4.000000001. I don't have to write that. Okay. We're going to jump over 4, and we're going to use numbers like negative point. We go x squared plus 1. Think about that. My hope is that eventually we can look at this and answer this question maybe a little bit quicker than actually going through the math. But if we just end up seeing a question like this and become robotic and just start doing stuff without really thinking, without foreshadowing what my math is telling me, maybe some of you get to the point and say, well, I know domain, first of all, we're going to assume that it's all real numbers, and now I'm going to take the bottom and say it can't be 0. Nothing wrong with doing that, but what's going to happen is you're going to waste a little bit of time doing it, especially when this gets a little bit more complicated. Would you agree that? Subtract 1 from both sides. And now we're square root both sides, right? So we get x equals plus or minus square root of negative 1, which that means x cannot be plus or minus I, right? Okay. Well, does I belong to the real numbers? No. Okay. So we go through all that math, and the only thing we kick out is an imaginary number. Well, that's fine then. If I assume that all real numbers existed for this, okay, and I don't kick out any of those real numbers, shouldn't my domain still be all real numbers? Okay. So domain is all real numbers. And a lot of times, WebAssign is going to say that is your domain, write it that way. Okay. But my hope is that you look at this maybe initially and say, okay, if I have x squared plus 1, and I think about any number that I can ever imagine from the real number line, and I square it, okay, what kind of number do I get back? I get either a positive number or, what's the one number that I would not get back that would be positive? 0, right? And 0 we just classify as non-negative. Okay, we don't want to necessarily say it's positive. We know it's not negative. So I'm either going to get a positive number or a 0 back. If I add 1 to it, doesn't it take everything and make it a positive number? Okay. So I'll always have something divided by a positive number, and by our rules of division, we know that's always going to yield some type of ratio. Okay. You'll never have division by 0. And that's the hope, is that you look at that real quick and say, oh, that can't be 0. There's never a situation where that bottom can be 0. All real numbers is my domain. Okay, and go to the next problem. Right. I don't want us to spend, hopefully, as we progress through the year, don't want to spend a lot of time on doing that type of work when it's unnecessary, I think. Okay? But that's the thing, and we saw that. I'll give it back to you in a little bit. That quiz that I gave you guys on Friday. Like that bottom one was something like this. And I saw a lot of people going through and doing work and getting 2 solutions. Okay? Not really knowing what those solutions meant. They were extraneous solutions, so when I plug them back in, I get a positive number here equal to a negative number here. I get like positive 3 equals negative 3. That doesn't work, right? So cancel both those solutions out. Some people actually substitute and cancel them out. My hope is we look at that right away and say, oh, absolute value can never be negative. And we say no solution, go to the next problem. Okay? So and people did that because they got in the mind frame of knowing the rules, applying the rules, but not really knowing when it's appropriate to use those rules, and not necessarily maybe that's not the best phrasing. Maybe they don't know exactly what those rules are referring to, when you should use them, when you should not use them, what the math really means. Okay. What if I gave you something like this? Let's say we change our function to g, and I give you square root of 2x minus 10. Square root of 2x minus 10. This is the second kind of dominating domain issue. Okay? Is when we take square roots or 4th roots or 6th roots or 8th roots. Okay? Any root that is even, we have issues. Okay? Because we can't take the square root of what kind of numbers? Negative. Okay? And then for the same reason, we can't take fourth roots of negative numbers. We can't take sixth roots of negative numbers. Can't take eighth roots of negative numbers. Okay? So whenever that number there is even, we have to think about forcing that amount there to be a positive number. Okay? Or 0. Because you could take 0 and multiply it by itself 2 times and still get 0, right? So you can take the square root of 0. Alright? So what we want is to take this number here. Okay? And you told me it cannot be negative, right? 2x minus 10 cannot be negative. Okay? Well, if it cannot be negative, how do I write algebraically not negative? If something's not negative, it's positive. Okay, so less than 0 would be negative, right? So what would be positive? Greater than 0. If I do that, that's taking this expression and saying it's got to be greater than 0 or it's not negative, right? Okay. But we can also have it equal to 0 because I can take the square root of 0. All right. So taking that inequality and solving that inequality, we should be able to now figure out what our domain values are that we can take the square root of. Okay. So if I go through and I start graphing this, or not graphing, solving. I was thinking about showing you the graph here in a moment. Add 10 to both sides. Divide both sides by 2, right? So we just, when it was division, we kicked out one number or 2 numbers, or it could be 3 numbers, whatever. Here, we just kicked out an infinite set of numbers, didn't we? We just kicked out everything that's to the left of 5. Okay? So graphically speaking, if 5 is there, those are the solutions for the domain. Those are the values that we're allowed to plug in here and get something back. Okay? So in interval notation, that first number is 5, and the last number would be infinity. That is our interval notation. If you wrote it in set notation, maybe you write domain x such that x is an element of all real numbers, but x is greater than or equal to 5, something like that. Or if you want to wipe that away and just write x such that x is greater or equal to 5, I'm okay with that. Those are the values that we can think about. Now, plug some values in, just to verify, make sure this works. If I plug 5 in, I get 10 minus 10, right? Well, that's 0. If f of x being 5, my f of x value is the square root of 0. And we can do that, right? We take square root of 0. Okay? People always ask, well, how do you know you take square root of 0? Remember, square root, like if I have square root of 2, I'm thinking about what number do I multiply by itself twice to get that 2, right? Okay? Well, if I have square root of 0, is there a number that I can multiply by itself 2 times to get 0? Yeah, 0, right? Okay? So you can take the square root of 0. If you forget that, grab your calculator, type in square root of 0, and it will say 0. It'll give you a solution. If you can't do a rule, a lot of times your calculator is programmed knowing that that rule cannot be violated. Okay, so if you try it, if I type in square root of negative 10, if I don't know I can't take square roots of negative numbers, it will come back and say non-real solution or something like that. If I plug in 6, I plug in 7, whatever, that's going to give me a positive number. You can take square root of a positive number. But if I choose a number like negative 10, okay, gives me negative 20 minus 10, negative 30, square root of negative 30, gives me something imaginary, right? It does not give me a number from the real number line, so that's why those values got kicked out. Okay. What about, I'm not going to change this very much. I'm going to make this a 3. Now, I don't know what number would do this, but potentially, can I get a negative 8 underneath that cube root? Now, remember what that means. Now you're thinking about a number that you multiply by itself 3 times to get negative 8. Can you do that? Is there a number like that? Yeah, negative 2 times negative 2 times negative 2 gives me negative 8, right? Okay. So, x, okay, this quantity here can show up to be a negative number, right? So in the last one we said 2x minus 10 had to be greater than or equal to 0 because we knew this number could not, this expression could not be negative for a square root. But it's allowed to be negative for a cube root. So when I get a cube root, domain, all real numbers. Nothing gets kicked out. Okay? Because you can take the cube root of negative numbers, you can take the cube root of 0, and you can take the cube root of positive numbers. Okay? What about the fifth root? Same thing. Seventh root, same thing. Ninth root, same thing. Okay? And that's the nice thing about some of the things that we deal with is that, cube root, fifth root, seventh root, they're all different types of functions, but they have very similar characteristics, features that we can kind of collectively say exist for that entire group of functions. Let's do this one. Let's go. Let's say I give you f of x equals 3 over square root of x plus 1. Okay? No issues up top, right? There's nowhere to put anything in. Okay? But the denominator can never be what number? It can never be 0, right? Okay? Likewise, the square root can never be negative. So if I can't have 0 and I can't have negative numbers here, hopefully you look at that square root and say, oh, well, it has to be that, right? That's the question we just did with the square root. We said it had to be greater than or equal to 0. But now because it shows up in the denominator, it can't be the 0. You got to get rid of that equality. Okay? So now we'll say x is greater than negative 1. And my domain then is negative 1 to positive infinity. Those are the only values you're allowed to plug in. Because if I plugged in a negative 5 here, I get an imaginary result for the denominator. If I plug in negative 3, same idea. If I plug in negative 1, I get 0, division by 0. That's a problem. But anything in this range, if I plug in 1, or 0 for instance, I get 3 divided by 1. That gives me an output value of 3, right? Okay. So inside this value, these values here, starting at negative 1, or I guess just to the right of negative 1, we start getting output values spit back to us. Okay. What if we did something like this? Let's say f of x square root of x plus 2 over, let's just go x squared minus 9. Okay. Do you have problems up top? Are there numbers that you can't take the square root of? Yeah. Okay, so we need a top to be greater than or equal to 0, right? But we need the bottom to not equal 0, correct? Would you guys agree with that? Okay, so the top has to be that. The bottom has to be that. Okay? And for us to get an output value, both those pieces of criteria have to exist at the same time. Okay? You can't choose, let's say I have, this is going to give me x greater than or equal to negative 2, right? Okay? This is going to give me x cannot equal plus or minus 3. Okay? I can't say, well, I'm going to choose a value from here, maybe 3, and say 3 is going to work. Because 3 does work up here, right? Square root of 5 is something you can do. But can I take square root of 5 and divide it by 0? No. So this needs to be true, and that needs to be true. Okay? So when I graph that, if I try to think about the things that I'm trying to put together here for my interval, okay, x is great. I'm looking for the overlap. X has to be greater than or equal to negative 2. So I put negative 2 in there, and then negative 3 and positive 3 have to be excluded. Well, negative 3 is over here. It's already excluded from this inequality. Positive 3 would be here. I need to exclude that. So I go negative 2 to 3, union 3 to infinity. We'll talk more about that type of question tomorrow. There should be an assignment website you can finish. And hopefully maybe 1 or 2 of those we can talk about in class tomorrow.